Good afternoon, everybody. Welcome to a wonderful Wednesday afternoon of Chem 170 Organic Chemistry with your host, me, Dr. White. All right, we got a lot to do, and you're going to get out early today because it's a lab day, and we do that on lab days. Now, the first thing I want to talk about is a week from tomorrow will be test number 2. It's summer, and things start happening quick. So make sure you have your safety belt on your chair. No, I'm just kidding. Oh, that's awful. I'll promise never to use that bad joke again. But things are going to speed up. All right, thumbs up, people. Do you see test Chem 170 test 2 information on your screen? Thank you. All right, let's take a look at this. This was posted this morning, and you should have gotten an email. On Thursday, the 8th of July, I will give test number 2 online. Just like test number 1, you'll be downloading a password-protected PDF file for test 2 from the assignment area D2L. That will be available next Wednesday afternoon. And on Thursday, right after class, around 4 o'clock p.m., I will send out an email with the password for test number 2 PDF file. You have until Friday morning, 10 a.m. to finish test number 2, upload your answers to test number 2 in the assignment area. It should take you about 45 minutes. If I were in a face-to-face, I usually give the students 50, sometimes 55 minutes. That's it. If you need up to an hour, a couple minutes over that, that's okay. Now, test number 2 has 9 pages, 10 problems. Some of the problems are multiple part. It will cover the functional groups alcohols, thiols, ethers, ethylene oxide, which is not a functional group, but the reactions of ethylene oxide, which is the only epoxide functional group I talked about, and aldehydes and ketones. Excuse me. And the points breakdown for test number 2, general knowledge, 11 points. Nomenclature, 34. Reactions, 60. Remember, nomenclature questions, there are 2 types. Here's the structure. Give the IUPAC name. Remember, IUPAC stands for the official name for you. For me, I also know is IUPAC, International Union Pure Applied Chemistry. I think it's cool to say that, so I do. And the second type is, here is the name, draw the structure. Now you've learned some common names. So in the second nomenclature question, I can also give you common names. And finally, you notice a lot more points this test than the first test because we're spending more time on reactions than nomenclature. Reactions, 60 points. There are 2 types of reaction. The bulk will be give the organic product or products for the following. There'll be usually about 3. I've got to write it this weekend. Synthesis problems, give the starting materials. The tests, like all my tests, are not open tests. I will do a review for test number 2 next Tuesday in our Zoom meeting. And as we've done this summer, we'll have our regular Zoom meeting for our lab and other material. And afterward, we will have, or you'll have, get the password for test number 2. So again, it will cover the functional groups, alcohols, thiols, ethers, and then the specific epoxide, ethylene oxide reactions, aldehydes, and ketones. And if you look at it, adds up. Oh, wrong thing. It has 5, yes, 5 bonus points. See what a nice person I am? And the best way to study for it is do the practice problems. You've learned from test number 1 why I call them practice problems. And the same will be true for test number 2. Any questions about test number 2? I guess not. All right. Today I promised I will be going through now the alcohols problem set. Then If we have some time, I'll go to carboxylic acids. We started yesterday, and then we'll take a break, and then we'll have our lab. And today's lab is ketones and aldehydes. Dr. White's sad because you don't get to do it hands-on. You'd have a fun time, but you'll still get the mental exercise about the lab. All right. Don't forget tomorrow, I will do the epoxides and ethers, or ethers and epoxides, really ethylene oxide problem set. And let's get going. In light of what happened yesterday, thumbs up, people. Do you see the alcohols practice problem on your screen? Thank you. All right, give the IUPAC name for the following. How do you do that? You find the longest chain or ring that has the hydroxyl group, that's OH, has a carbon with the hydroxyl group on it, name it as an alkane or cycloalkane, and then drop the E at OL. For acyclic, not in a ring, you need a number of what carbon that is the hydroxyl group is on. For ring, no number, because for this class, when there's only one functional group in a ring, which I will do, the hydroxyl group is always one, and everybody knows that. Now, I'm going to go through a couple on here. Let's look at B. What do we have? Remember, you should look for what's different. What's not a carbon-carbon single bond, carbon or hydrogen atom should get your attention like that. And oxygen with a hydrogen on a carbon. It's a ring. How many carbons? 6. Cyclohexane. Don't forget the cyclo when it's a ring. Drop the E, add OL, cyclohexanol. No number because it's on a ring. Now, if we look at C, hydroxyl group on a carbon. What's the longest chain? 1, 2, 3, 4, 5. And what carbon is the hydroxyl group on? You give it the lowest number, meaning it's the carbon closest to the end of the chain. You always start numbering at the end, 1, 2. It's on carbon 2. If you want the other way, be 1, 2, 3, 4. And I hope you all agree 2 is smaller than 4. It is. And therefore, it's 5 carbons is the longest chain, 1, 2, 3, 4, 5. Pentane, drop the E, add OL, pentanol. And what carbon is the hydroxyl group on? Carbon 2, 2-pentanol. Oh, look, it's your old friend, the methyl group, and it's on carbon 3, 3-methyl 2-pentanol. Now, if we look at D, we have, a ring and a lot of other stuff. What's different? Hydroxyl group on a carbon of the ring. How many carbons in the ring? Count every bend. 5. Pentane, ring, cyclopentane. Alcohol that has the hydroxyl group on the ring. Drop the on cyclopentanol or pentane, and you add OL, you get cyclopentanol. This carbon is 1. We don't put a number on it. And going clockwise gives you the lowest numbers. On carbon 2 is an isopropyl, and carbon 3 is a methyl. Now I have 3-methyl, 2-isopropyl, cyclopentanol. If you had written down 2-isopropyl, 3-methyl, cyclopentanol, don't tell the IUPAC, please, but I give you full credit. So I'm not holding you to the alphabetical rule. All right, that's one type of nomenclature question. The other type is draw the condensed structure for the following molecules names. And you always start on the right and move left. So if I look at B, OL ending tells me alcohol. If that were an E, cyclobutane, well, you call it a square, but we call it in organic chemistry a ring. And on one of the carbons, doesn't matter which, you have a hydroxyl group. Now, if we look at C, 3,5-dimethyl-2-octanol, start at the right, move left, and what do you have? OL ending, alcohol. That were E, octane, 8 carbons. Now, as I told you, good habits, Dr. White will never break. So I always start counting from the right to the left. for alcohols and other functional groups with an oxygen in it. You could have written it the other side too, but I don't. Both will be correct on the test. And on carbon, where is the hydroxyl group for the alcohol? On carbon 2. This is 1, this is 2. Then methyl, CH3, di 2, where is it? On carbons 3 and 5. And don't forget, there's always 4 bonds to carbon. Now, D is interesting. And here we have para-isopropyl phenol. What's phenol? That's a benzene ring with the hydroxyl group. And it's just like toluene, that OH is considered a substituent on a benzene ring. So if that's 1, para is 1,4, meta 1,3, ortho 1,2. The isopropyl group is in the 4 position. And for those who like, and I saw some of you did on test number 1, like to use the total line method. You could also write it as it's written on this page on the right with the line method. Common name, ethyl alcohol. Ethyl is the R group, CH3, CH2, and alcohol means there's a hydroxyl group. And finally, let's do G. And what do we have? 2-methyl, 2-propanol. Start from the right, OL ending, alcohol. That were an E. Guess what? Propane, 3 carbons. And carbon 2 is the hydroxyl group. And it's your friend, the methyl group, your good buddy. And that's on carbon number 2. By the way, this molecule has a common name, T-butyl alcohol. All right, now for reactions, you have give the organic product or products for the following reaction. You don't have to ever balance equations. I saw one of you do that for the combustion, but you don't have to. All right, look for what's different. How do you make an alcohol? Take a double bond. What's different? This reacted with acid and water. This is the only reaction I have on 2 tests. It was on test 1, and it can be on test 2. Break the pi bond. 1 carbon gets CH, the other gets the OH, and it follows Markovnikov's rule. The carbon with the most hydrogen gets the hydrogen from water, the other carbon gets the hydroxyl. And here, I'll just do 1. This carbon has 2, that's 1. Break the pi bond, do you break carbon-carbon single bonds? No. So I have 4 across, and this carbon gets the hydrogen, this carbon gets the hydroxyl group, and you've made an alcohol. And similar for B and C. Well, I gave you a lot of practice. All right, now this one's a little tricky. And D and E were a trick of mine. Now, what's the reaction? Let's look at E. You have sulfuric acid, H2SO4, and the little triangle means heat. Sometimes I do and sometimes I don't write 180, which tells you you're heating pretty high. And what happens, here's the general reactions, dehydration of an alcohol to make a double bond, alkene. It follows Zays's rule. Zays's rule is you get the double bond that has the most carbon atoms bonded to the carbons of the double bond. And you need a hydroxyl group on a carbon, an adjacent carbon with a hydrogen, because you're losing water. Let me say that again, because it's important. You need a hydroxyl group on a carbon and an adjacent carbon with a hydrogen. Now, if we look at D, here's my hydroxyl group. There's 1 adjacent carbon here with 2 hydrogens, but this one with the 2 methyl groups has 0. And that was a trick by Dr. White, because you don't have to worry about Zays's rule. There's only one place it can go, to the double bond between the hydroxyl carbon with the hydrogen, and that's what you get. And D was like that too. But let's look at F. F, we have an alcohol or reacting with sulfuric acid and heat. Notice the carbon with the hydroxyl group, you have two adjacent carbons with hydrogens, A and B. If you lose the hydroxyl group and a hydrogen from A, you'll get this compound A. If you lose the hydroxyl group and the hydrogen from B, you'll get this compound B. Now, which one has more carbon atoms directly bonded to the double bond carbons? In A is 2, I've circled them. In B is 3, which is a greater number. Hopefully you all pick 3. And therefore B is the correct answer. You don't get A the way I teach it in reality. You get about 90% B and a small amount of A, maybe more B. All right, next ones. Oh, look, you've got an O in a bracket. What does that mean? Oxidation. Good news, I'm not having you memorize different oxidation reagents. I'm just using the general way organic chemists do that. And here we have a secondary alcohol, oxidize it. Secondary alcohol, lose the hydrogen from the carbon with the hydroxyl group and the hydrogen from the hydroxyl group and form a carbon-oxygen double bond. And you make this ketone. And same thing for H. And I, we have a primary alcohol. If you lose the same thing, hydrogen from the carbon with the hydroxyl group and the hydrogen from the hydroxyl group form a carbon-oxygen double bond. Remember, you do not break carbon-carbon single bonds. You form an aldehyde. Now, reactions of alcohols, you take thionyl chloride, SOCl2, react it with an alcohol, and sometimes I can put it like plus or above the arrow, same thing. You replace the hydroxyl group on the carbon with the hydroxyl group with a chlorine. And I give you a couple examples, like K, here's the hydroxyl group. I replaced it on that carbon with a chlorine. Everything else comes along for the ride. And now another way of doing similar is if you take an alcohol and react it with HX. And I don't have it here, but X can be chlorine, bromine, or iodine. And if we look at this ring here, M, which I got my spacing wrong, rare, but it happens. What do we have that's different? Ooh, it's a big, scary molecule. No, you look for what's different. What's not carbon or hydrogen? I mean, carbon or hydrogen should get your attention like that. Hopefully that did. And oxygen, hydrogen, hydroxyl group, HCl, HX. Remember, X can be chlorine, bromine, or iodine. You replace the hydroxyl group with the halogen on the carbon that has the hydroxyl group. In this case, HCl, X is Cl. Everything else stays the same. This carbon has the hydroxyl group. This is a carbon with the chlorine. And I give you 4 more examples. And in case you didn't get it the first time, I realized, I should put another Zaysesrol dehydration problem. And Dr. White was too lazy to re-alphabetize everything, so I popped it on the end. And this is how you do it. You can lose a hydrogen from A in the hydroxyl group and get compound A. You can lose a hydroxyl group and the hydrogen from B, and you'll get compound B. A has 2 carbon atoms directly bonded to the carbon's double bond. They're circled. And B has 3. And Zays's rule, the way I'm teaching it, is the product you get is the one that has the most carbon atoms directly bonded to the carbons of the double bond, which is B. All right. Any questions about alcohols? Oh, I got a question for you. Did anybody happen to drive by a gas station and think the gasoline they sell has an alcohol? Okay. Did anybody happen to pick up a bottle of hard spirits, like the good stuff, vodka, and see It's got ethanol in there. That's an alcohol. Did you pick up a bottle of rubbing alcohol and see it's got 2-propanol, otherwise known as isopropyl alcohol, which is an alcohol? I'm going to have to work on you people. I will not give, oh, let's try one more. Did anybody look at the nail polish you use and see it's got acetone, and that's a ketone? Remember, organic chemistry is all around you. I stole that from SpongeBob. And it won't hurt for you to think about it when you're not in my Zoom meeting. Trust me, I'm a doctor. Did that work? How about trust me, I'm a chemist? Did that work? All right. With that, let's go back to carboxylic acids. And we're talking about nomenclature, how you name them. And what you do, you find the longest chain. Remember, this is going to be on test 3, not test 2. You find the longest chain of the carboxylic acid that has the carbonyl carbon. Remember, carbonyl carbon, carbon double bond to oxygen, and you name that as an alkane. That alkane name, you drop the E at the end, and you add OIC in the word acid. Note the carbonyl carbon is always number 1. Can't have it in a ring of carboxylic acid. And you name and number all the other substituents, just like you've always done. And number 5, I'll never put on the test. So let's do some more of these. All right. All right, why don't you give the IUPAC name for the following molecule? 3 points each. Your turn. And then afterward, I'll tell you what an evil, nasty, terrible molecule this is. Just briefly, and later on, I'll give more briefly why it's so evil and nasty. And when you're done, give me a thumbs up. Well, for those who finished early, let's give everybody time to finish. I think everybody's done. So what do? You look at a molecule, look for what's different. Ooh, oxygen here, double bond to carbon, hydroxyl group to that same carbon, and carbons here. What do we have? A carboxylic acid. And how do you name it? You find the longest chain with the carbonyl carbon. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Well, 6 is greater than 4, and 6 carbon is hexane. It's a carboxylic acid. Drop the E, add OIC, and the word acid. And remember, this carbonyl carbon is always 1. Everybody knows that. And then on carbon 2, I have an ethyl group. And that's 2-ethylhexanoic acid. And I'll explain more detail why, but this was an impurity in a feedstock used for a chemical reaction I had invented, and I didn't realize in a new lot or amount of this chemical we got from a reputable supplier, it had all this impurity, And it caused me about 6 weeks of, oh, how should I put this politely? Tremendous grief. I could use other words, but we don't do that in a classroom. And it was bad. All right. Oh, let's do one more. And the question is, what's the IUPAC name for that product? I don't think I've ever written that one before. You people write it down in your diary today. Dr. White used an example he's never used before. Not, you don't have to. I see one person done. Two. And I think everybody's done. So I'm going to get to work. We'll look at a molecule, what's different, look for what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond, oxygen here, double bond to this carbon, same carbon has a hydroxyl group. What is that? And we have carbons here. We have a carboxylic acid. And what do you do? Find the longest chain that contains the carbonyl carbon, carbon double bond to oxygen. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So 7 is greater than 6. 7 is an alkane, would be heptane, and it's a carboxylic acid. So I'm going to get rid of the E and add OIC and the word acid. Am I done? No, as soon as I say heptanoic acid, that's all spoke. Oh, I've got two of our favorite group, the methyl. And how do we say to di? Now, even though they're on the same carbon, when you have two of the same di, that tells you need two numbers. So this would be 5,5-dimethyl heptanoic acid. Say that 5 times quickly. No, you don't have to. Now, there are two types of nomenclature questions I ask. One is give the IUPAC name from the structure. The other is draw the structure for the following name. So let's do one. And I'll do the first one, then I'll let you have some fun too. And the question is, how do you decode this to draw the structure? Start from the right, move left. OIC acid immediately tells you carboxylic acid. If this were an E, that would be 8 carbons, octane. And I'm going to put my carbonyl on this side. You could have put it on this side too. I don't. This is my good habit that I won't change. And I have both a hydrox group and a carbon double bonded. Now I keep on going. Oh, on carbon 2 is a T-butyl group. This is 1, this is 2. And now I know there are 4 bonds to carbon. So I'm going to put in my hydrogens. Remember, it's your solemn responsibility now. If I make a mistake putting in hydrogens, let me know so I can correct it. And that's how you do it. 2-T-butyl octanoic acid. And that's how you do drawing the structure from a name. Well, 2 days later, I finally got the name down. All right, draw the structure for 2-methyl-4-N-propyl decanoic acid. Enjoy. Don't forget, my office hour tonight is from 5 to 6. If you have any questions, stop on by and say hello, and I'll answer your questions. And don't forget when you're done. I see people showing me their thumbs. Thank you. I guess everybody's done, so I better get to work. How do you decode this to know what to draw? You start from the right and move left. OIC acid, that's a carboxylic acid. Carbonyl hydroxyl group, R group, and that's a carboxylic acid. And if this were an E instead of OIC in the word acid, decane, 10 carbons, I better get to work. And at the end carbon, I always do it on the right. You could do it on the left too, but I don't. I have my carboxylic acid. And this is carbon 1, 2, 3, 4. On carbon 4, I have an N-propyl group. That's 3 carbons onto the N carbon. And carbon 2, I have a methyl group. And that's how you do it. And that's how you name carboxylic acid using IUPAC rules. Now, as I said, we're getting into more, how should I say this, mature functional groups, those that have been around long before IUPAC, and certain common names are still being used. And so there are a few I'd like you to learn. All right, thumbs up, people. Does everybody see common names for carboxylic acid? Thank you. Now, the first one is formic acid. Now, remember, a carboxylic acid has this structure, but like formaldehyde, R can also be H. This is an exception, and that's formic acid. Formic acid has this structure. Now, the IUPAC name would be methanoic acid. I have to think a while because nobody ever calls it that. Everybody calls it formic acid. Now we're getting to the part of the semester or I can show you, where do you find this stuff? Why am I learning about this? Good question. Thank you. How many of you have ever heard about the fire ants? And the fire ants, and I hope I never see one, they're down south in Texas and around there, I guess. I'm not sure. I'm not a chemist, not aware of the bugs in the United States or ants. But fire ants are called fire ants because they have a defensive weapon that when they're attacked, they spray their attacker with a liquid. And if you get it on yourself, it feels like you've been burned. A fire has been applied to your skin. And that's how they got the fire ant. Well, how do they do that? Well, it turns out Mother Nature, who's the greatest of all organic chemists, the fire ant sprays a solution of hot water and formic acid. And what you get is called an acid burn. I hope you never have this happen to you. I never have, but in a teaching lab, I did have one student have this happen to him. You get a strong acid on your skin, it burns. The sensation is like if you touched it with hot metal. And afterward, the damage to your skin looks like if you had been touched with a bar of hot metal. That's why they call it an acid burn. And that mixture of formic acid and water, the fire ant burns its whoever is attacking it. That's quite a good weapon, I guess. Now, let's look at this molecule, acetic acid. And acetic acid is is a methyl group. And this is the structure of acetic acid. Nobody ever calls it, except to say nobody ever calls it ethanoic acid, which would be the IUPAC. It's acetic acid. And that's where you have a methyl group as the R in this carboxylic acid. Do you know you all probably have acetic acid in your house? What? Yeah, you do. No, I don't. I'd know if I had acetic acid in. Well, you do, and let me show you why. You probably have it in there. If you take acetic acid, and this is stuff you should know, switches on for this slide. About 4% acetic acid and about 96% water. You mix it together, you get a homogeneous solution, and you know what we call that solution? Vinegar. Vinegar is acetic acid and water, a dilute solution of acetic acid in water. So if you have vinegar in your house, and I have both white and apple cider, and also Japanese, the Marukan rice wine vinegar is awesome. And I think I have some regular wine vinegar too, not much. I'm more into apple cider vinegar. But anyways, all of them have the same thing, acetic acid and water. They just have some minor other constituents that give it its different flavors. Now, if you look into your refrigerator, you'll find pickles, if you have that, ketchup, mustard, and in Chicagoland, you know that glow in the dark green relish that I love for your hot dogs, and those all contain vinegar. So whenever you're putting a condiment on your hot dogs, hamburgers, or French fries like ketchup, you're putting acetic acid on there. But you didn't think about that. Organic chemistry is everywhere. Now, the last one I'd like to talk about is benzoic acid. And again, carboxylic acid, carbonyl hydroxyl group, R group. Benzoic acid is both the IUPAC and the common name. And similar to benzaldehyde, that's when R is a benzene ring. and this is the structure of benzoic acid. So on a test, if I asked to give the IUPAC name of this one, this benzoic acid, if I asked you to draw it for any of these four, you should know how to do that. And like I said, look around your house, look at labels. You'll see a lot of what I'm talking about, especially by the end of the semester, are on things you buy and use in your daily life. All right, switches off for this slide. We'll talk more about it in the chapter on fats and oils, but there's certain key long chain acids where N, this carbon plus these carbons plus this is very long. If you have 12, and nobody calls it, that would be dodecanoic acid. I have to think about it. That's got a common name called lauric acid. And palmitic acid is 16, stearic is 18, and oleic is 18 with a double bond. But these I'll talk more about. But I should warn you, I worked at a company where I was the laboratory manager, and they made the most stearic and oleic acid in the United States. And one of the things I did was come up with 2 new grades. I'll talk more about it later in the semester of oleic acid, and they're still selling them. Those grades, because those are for cosmetics. A lot of these are used in your personal care items and cosmetics. All right, switch is still off. Now, Mother Nature does some amazing things with what's called hydroxy acids. And in life, you can stay away from it in this course to make your life easier. But in real life, we have molecules with more than one functional group. And this will never be on test, but I thought it'd be cool to talk about. Now, lactic acid has this structure. And notice I have it this way. My software likes writing it this way. Another way of writing it, you do not have to know this. The IUPAC name, and I haven't taught you with different functional groups, but this would be 2-hydroxy propanoic acid. You name the acid hydroxyl group as a substituent. But anyways, this is lactic acid. And have you ever heard the term, especially if you watch Running Man by Schwarzenegger, no pain, no gain, which is really wrong. I learned that from my physical therapist a long time ago. But if you work out real hard, you know how you get that pain in your muscles? That's caused by lactic acid. That's what's causing that burning. I guess that's Mother Nature's way of saying, hey, slow down, you're ruining your muscles or whatever. Remember, I'm a chemist, not a medical doctor. Now, I'm going to start getting into stuff you won't believe. And I'm doing the chemistry, and in no way I am doing any moralistic stance on it. Now, one of my, I don't know if I'd call it a hobby, but mental games I play is when I see a product, I wonder, how did they do that? And I think, isn't there a TV program on, I think the History Channel, how did they do that or something similar? How did they make that? And a while back, a certain company called KY that made a lubricant for certain personal activities. I think you know what I'm talking about. If not, look it up. Came out with a new product. And that product, this is a couple of years ago, a number of years ago, was a warming gel. And you put that warming gel on certain personal parts of your body for certain personal activities, and it caused those parts to get warm. And I wonder, how are they doing that? It got my interest. So I went to my local, at that time, I think I went to Walmart, and they had that product on the shelf. I picked up the box, I started reading the ingredients label. All of a sudden, oh no, that's how they're doing it. And in the ingredients label was near the end, lactic acid. And they put a small amount in there, When it got rubbed into your skin in a personal spot, the warming was a very, very, very mild acid burn. Well, they must have had problems with it because they've since changed the formulation. And now they have a special alcohol. When it interacts with the moisture on your skin, that causes heat to be formed because it's called hydration of the alcohol. Now, I've sort of figured out, and I won't talk about it now, a couple years later, they came out with another lubricant that was called fire and ice. I knew how they did the fire, and it took me a while to figure out how they got the ice, making it feel cold and warm at the same time. Didn't realize organic chemistry can be that interesting. It can. Now, another carboxylic acid or hydroxy acid, and actually it has 3 carboxylic acids, and I could rewrite it this way. And you do not have to know the structures of this, but I thought it'd be neat to see it because it's in our everyday life, and that's citric acid. And if you notice, citric acid has 1, 2, 3 carboxylic acids. And it also has an alcohol, hydroxyl group. And citric acid is the molecule in lemons and limes that gives it the sour taste. Have you ever bitten into a lemon or lime, or especially a lemon, or had real sour lemonade? You go, ooh, is that sour? I'm not a big sour, heavy sour person. Well, what makes it sour is the amount of citric acid. Limes are more sour than lemons because they're more citric acid. Now, citric acid itself is a white solid. And organic chemists found a way how to isolate it and make it. And if you got the credit and the credentials, you can call up a company and they can deliver by next week 50, 100,000 pounds to your house. Now, I'm not going to do that because I don't use it. A couple of years ago, I figured I'm going to try using citric acid in some of my cooking to make sweet and sour. So I bought some citric acid from the spice house. It came and I wondered, how sour is this? So I went like this into salt. Went, oh, is it sour? Now, how many of you are familiar with it's not new anymore. It's been a while, maybe 8, 10 years, the trend in children's candy that they make it super, super solid, like the rings that are lollipops or the drinks that are, I don't like it, but super, super sour. How do they do that? They just load it up with citric acid that they can buy. And no, they don't sit there squeezing lemons or limes. And that's how they do it. I'm not a big sweet, super, super sour candy person, never am. Give me just the plain sweet stuff. By the way, my favorite dangerous candy, a couple of them are, let's see, any white chocolate uh, and Nestle's Crunch. I shouldn't be thinking of this. Stop it. All right. And if I look at the clock, it's about time to take a 5-minute break. So let's take a 5-minute break, come back, I'll introduce you to lab, and then I'll let you go. And with that, I'll see you in 5 minutes. Oops. All right, give me a second while I open up the lab. All right, let's get going. It's lab time. And today's lab is aldehydes and ketones. And let's take a look at the lab. Don't forget, the lab you did on Monday is due today. And if we look, we have the thumbs up, people. Do you see aldehydes and ketones lab on your screen? Thank you. All right. We're going to do, and you'll see a lot of the labs are similar. And this will give you a hands-on understanding if we were in the lab at ECC. Just some hands-on. First of all, I'm going to look at the solubility of aldehydes and ketones in water. And remember, This is an aldehyde. And if we were in lecture in the lab room, we have a dry lab room right outside the actual lab, I'd be writing this on the board. And this is a ketone. And both have a carbon double bond to oxygen. Now, the first one is solubility. And what you do is take a test tube for each one that's being tested, each chemical, fill it with DI water. DI means deionized. We have filters at ECC, and most labs do, that take the ions out of water, tap water, or we say in industry city water, to make it pure. You don't want the ions messing up things in your experiment. And to each test tube, you add some of the aldehyde or ketone. They're all liquids, so that's why I have 5, 10 drops. You mix up the test tube, never with your thumb like that. Hold it, hit it 5 times, and then see if it's homogeneous, the same throughout, or you see separate layers. And if it's separate layers, it's insoluble. If it's one layer, it's soluble. And here I have a couple of ketones and aldehydes. Now, as you can see on the screen, for each of these underneath the name, I would like you to draw the structure of the compound. And I gave you the data because we're not going to have you do this at home. All right, the odor part, let's just omit. Now, the next thing I'm going to talk about is oxidation of aldehydes and ketones. And we're going to use potassium permanganate. And for potassium permanganate, KMnO4, is an oxidizing reagent. Now, to make this work, usually you have it in a little acid, acidic, so I'd have you wear gloves sometimes. Not that it's necessary. And let me remind you about something that I didn't teach you for the test, but it's important to know for the lab. And that is, if you have an aldehyde and you oxidize it with potassium permanganate, KMnO4, this is purple in solution. And when this is oxidized, you get the carboxylic acid from the aldehyde. It's converted to this. And you also get manganese dioxide. MnO2. This, if you remember from a previous lab, is a muddy brown color. Sort of like if you take dirt and get it wet, and dirt from certain parts of the United States, best way I can call it is a yucky, muddy brown. You don't have to put the yucky down. And if you have a ketone and you oxidize it with potassium permanganate, KMnO4, it's still purple. But here, ketones cannot be oxidized. No reaction. So this will stay purple. So this is a good way of distinguishing, do you have an aldehyde or a ketone? If you see muddy brown, you've got an aldehyde. If it stays purple, you have a ketone. And here I have benzaldehyde. I think you know what that is. And ONE ending in the second one is a ketone. And to make it interesting, we have unknown number 1. And you're going to have to, in one of the questions, identify as unknown 1 an aldehyde or ketone. And in real life, we would have that for you to test in the lab, and you get this result. let's move on. Now the final part. This is fun. This is called the crossed aldol. Now, crossed aldol was when you react two different carbonyl ketone or aldehyde, and this is a case. Now here we have two molecules of benzaldehyde reacting with one molecule of acetone, and here the solvent, I didn't put it down there, is ethanol. And you get this big molecule, which has the common name dibenzyl acetone. And if you notice, that's a big, fancy compound. Now, both before and here, I have where you can see this in YouTube. Let's do this one. Let's see how it looks. I forgot. Let me get all this commercial garbage, skip ads.
It's nice, yellow orange, it's a great one.
All right, I'm gonna, and what they've done is they've mixed the chemicals together. Now, in our lab, we don't use this called a magnetic stir. See how she's mixing? When you mix all the chemicals together, it's a liquid like that. And then after about 5 minutes of stirring, and you do it by hand, and this is an Erlenmeyer, you'll see a solid form. It's beautiful to see it. And they have either a cheap old magnet, or the person's got the stir going too fast. That's why it's not staying in the center. And after a little while, what you'll see is a solid in there. And you don't have to put any more in there. I don't know why they're doing that. And you see a solid, and you put it in ice. After 10 minutes, you'll put it in ice. That helps separate and create the solid from the liquid. Now, how do you separate a solid from a liquid? You use what's called a Buchner funnel. And a Buchner funnel helps you separate it. And that plastic white thing, or is it ceramic, is a Buchner funnel. Underneath, you're pulling a vacuum. See how the liquid is going to get sucked right through there? She's got the vacuum on. You can, they're using ethanol, you could use water. Now you're going to pour it all in, and it's got solid liquid. And notice on the filter paper in the Buchner funnel, the liquid is going underneath, and that solid is the dibenzyl acetone. And you let it sit there for a while to dry it out. And guess what? You can take the melting point of that. Unfortunately, we're not in the lab to do it. Now, if you notice, it's yellow. See how it's a yellow color? And I'll explain why in a second, maybe 2 seconds. Now, why is it yellow? If you notice, you have the benzene rings here with double bonds. Over here, you have a double bond between carbons, and you have a double bond between the oxygen and carbon. Now, if you remember, I said aromatic ketones can absorb UV light, and sometimes, I didn't mention then, with all those double bonds, it can absorb certain frequencies of regular from white light. And white light is made up of different colors. How many of you remember from high school, what are the colors of the rainbow? Roy G. Biv. I still remember that. Don't ask me why, but I do. Well, if this is yellow, what is happening? It's absorbing all the colors but yellow in Roy G. Biv, the colors of the rainbow. That's because all these conjugated double bonds. Now, in the lab, you'd take some benzaldehyde, this amount, mix it with acetone and ethanol, and then in the sequence I have here, and in Erlenmeyer, swirl it to dissolve. After you do that, you add the sodium hydroxide, that's this up here, you're in ethanol, and you swirl it. And all of a sudden you get those pretty crystals form, and then you collect it on the Buchner funnel and do the melting point. And if you were doing a lab, you'd have the melting point of this. It's a little below theoretical because in the lab, we don't have time to fully dry it. Remember the colligative effect. Now, time for Dr. White to have some fun. What's happening in this reaction? All right, everybody pay attention. This is called the mechanism, what happens step by step. Now, if you look at benzaldehyde, the alpha carbon has no hydrogens. It's on the benzene ring. So you cannot form an enolate anion with benzaldehyde. But acetone, you have two carbons, and each one can form the enolate anion. So the key step is the first step. When you react acetone with sodium hydroxide, you form this carboxylate, this enolate anion. I'm getting the last chapter we just talked about mixed up in my head. Stop that, Dr. White. Okay. And the enolate anion, like in an aldol condensation, will attack the carbonyl carbon of benzaldehyde. And it forms this enol, just like you learned in class. Now, what I didn't teach you is Mother Nature, or just in general chemistry, when you can have more conjugation, alternating single, double bonds, that makes a molecule more stable. Now, if you look over to here, the benzene ring has double bonds, and the carbonyl is a double bond, but in between, there's nothing. Well, I've got a hydroxy group here and a hydrogen there, and if I lost something, H2O, what's that? Water, I would form a double bond, dehydration. And whenever you can have a stable leaving group, and trust me, water is a stable leaving group, and form conjugation, boom, it's gone. And you lose water and form this new molecule. Now, the new molecule here, this carbon, CH3 attached to the carbonyl, has alpha carbon with hydrogens on it. So on that side, I can form this enolate anion, which attacks the second molecule of benzaldehyde. This attacks that to form this aldol condensation. And the same thing, hydroxy group of hydrogen. If I can lose that, water, I'll form a double bond, and now this carbonyl will be conjugated to the benzene ring, which makes it stable. And it does. And this all happens right before your very eyes. But the key step here you should know is acetone base sodium hydroxide forms this enolate anion. And in class, what I would do is tell students, you can take your cell phone and take a picture of this. So I only bring 1 or 2 copies. What I'll try and remember is post this as a download in D2L assignment area. And that's this, isn't that beautiful? By the way, Dr. White's an enolate or synthetic organic chemist. That's what I did my PhD work, much more complex than that. But anytime I see an enolate anion reaction, I'm happy. And I'm happy right now because I see it. So Here's the melting point. And then you have a bunch of questions, the one on odor, omit, and that's today's lab. Let me remind you, tomorrow I will be doing the ether epoxide problem set. Make sure you do it. I mentioned it the other day, but I'll mention it again. Test 1 is the test of the semester that historically has the highest average. Test 2 is the test of the semester that historically has the lowest average. It's the hardest, but it doesn't have to be. Last semester and a couple other semesters, it was quite high. Students studied. So how should you be studying? Doing the practice problems. And with that, I'm done. Gang gesund. Goodbye. I'll see you tomorrow. Same organic channel, same time. I was going to say same bat channel, same bat time, but most of you probably never saw the original Batman TV program with Adam West. But anyways, goodbye. Gang gesund.